Introduction to Time Domain Finite Difference Method. I'll start just by introducing the concept of time domain finite difference method. It's a bit different than what we've studied up to this point, and there's good reasons for that. And I'll demonstrate these concepts with sort of an example, but I'll set up how to solve the heat equation, the time domain heat equation, using the finite difference method. Introduction. So just like in almost all computation, it starts off with formulation. And this is where the equations are flying all over the place, and maybe it ends quite confusing. And we finish with implementation, where we pull out the key equations, and then we go step 1, 2, 3, 4, 5 of how your computer code would actually solve the problem given the equations you derived in your formulation. So in the formulation, in general, this is how it works. So the first thing is you would want to identify the governing equation. So for this example, it's the heat equation. In the next example, in the next video, we'll talk about solving electromagnetic. So our governing equations in that case is Maxwell's equations. From there, we'll take the governing equation and we will approximate all of the derivatives using finite differences. When we approximate the time derivative with finite differences, we're going to get the difference of a new value minus a previous value. And there may be several occurrences of that new value in your finite difference equation. So what you'll do is you will solve that entire equation for that single variable, which is the new value of heat, for example. So you'll solve it for the future time step, we call it. In this equation, you may notice that a bunch of constants have collected. And those constants, if they don't change over time, you will want to calculate them before your main loop. Because the way this is going to work, we're going to derive an update equation. And what we'll do is we'll update each point on your grid. That will take all of your function values from one instant in time to the next. And then we do it all over again and again and again and again, and you'll watch your function kind of move around and move and evolve. And so the technical words is we're integrating over time. But if your coefficients were a bunch of constants, maybe it's material properties, your time step value, other things that don't change, why keep calculating it? So we will calculate these constants ahead of time, and we'll use those in the update equation. So then we'll write the final update equation that way. And usually it's just a very simple equation at this point where new value equals some constant times the old value plus some constant times other information plus some constant times other information, and so on. Now here's how we implement it. But really what we come away with from the formulation is the update equation and how to calculate those coefficients that are in the update equation. We'll have a dashboard. This is where we define everything: material properties, sizes, how long we want the simulation to go for, what information we want to get out of it, and all of those hard-coded numbers. We'll then calculate our grid, how many points on the grid, the resolution of the grid. We then have to build our device onto the grid so that we know what we're simulating. Then we'll calculate the update coefficients, because very often information from the device on the grid goes into those update coefficients. Just before we enter that main loop, we'll initialize all of the unknown functions. So if we're solving the heat equation, that's temperature. If we're solving an electromagnetic equation, that's the electric and magnetic fields. Now see where we enter the main loop. Typically, we'll set the function to 0 everywhere. That's not always the case, but usually that's what we do, and then we start iterating. When all this is done and all the function values have moved across the grid and wiggled around and sort of settled into whatever answer we're trying to get, now the simulation's done. We will take the results from that simulation and post-process it to learn something. And usually the last thing is to visualize that. I don't like just looking at numbers on a screen. I much prefer to visualize and see pictures and plots and that sort of thing. I just want to go through some notes that I think are common to almost all time domain finite difference methods. And one thing is that implementing this does not require the use of linear algebra. Now, we certainly can use linear algebra. Many times there's a use for that, but we don't have to. It can really just be brute force code where we're setting up loops that iterate through our grids and do other things. Now, since it's avoiding linear algebra, time domain methods tend to scale very near linearly. A lot of papers will say they scale linearly, and I can make some good arguments where it's probably not quite that, but it's certainly close. A lot more closely than the finite difference method we've been studying, where let's say we double the size of the problem. Well, then our matrices have 4 times the number of numbers in them, and then the number of computations maybe goes up by a factor of 16, and it scales very non-linearly as the size goes up. Whereas with time domain, if I double the size of the problem, that really just means I double the number of points and I double the number of computations. So it scales linearly. So time domain is the go-to way for simulating very, very large scale simulations. And that goes back to scaling nearly linearly. If we employ matrices and we have something very large, those matrices can explode very quickly. So for very, very large things that we want to simulate on some supercomputer somewhere, almost always what's happening is a time domain simulation. Very often we're interested in the transient response of a device. And in fact, on the next slide, we talk a bit about what is meant by transient, but you can imagine at first your simulation is doing nothing and you excite it with some kind of pulse, and that pulse bounces around and sloshes around and all sorts of things are happening. But after a long time, all of this up and down wishy-washiness, whatever's happening, it kind of settles out and we get the steady state response. And if we were to employ the finite difference method that we've been using up to now, we really just jump straight to the steady state response and we miss everything up front. You're going to see this on the next slide, so I won't talk too much about that. But time domain simulations are great for simulating and seeing and visualizing the transient response of devices. If we have anything that's non-linear, whether it's materials or devices, or maybe there's diodes, that's very, very easy to do in a time domain simulation, very difficult to do in a frequency domain simulation, and sometimes impossible, but it's straightforward and very easy in a time domain simulation. And that's ultimately because material properties arise due to time domain phenomenon. So when we jump to frequency domains, sometimes that can become a problem. Nonlinear is certainly one, but it's very easy with time domain. Time domain is an incredibly good technique for learning if you're a student, because as you're simulating something, you're watching a heat wave interact with a device, or you're simulating an electromagnetic wave and you're watching that bounce off and interact with your materials on your grid. And it's hugely educational. And very often, if you don't know how a device is working, simply by watching how your waves or your heat or whatever it is you're simulating, watching how that interaction, what's happening, you can figure out what's going on in your simulation and learn. So it's a great tool for that. And I just mentioned that, great tool for learning about devices because of the visualization. So let's think about steady state versus transient response. This is an electromagnetic simulation. We have a slab of dielectric in air, and we've illuminated it with a pulse. So imagine turning on a flashlight. And some of that flashlight has now gone in and reflected. Some is reflected here. This up-down is the standing wave. And now you can see that the amplitude is a little bit uneven. That's because some of what reflected is now traveling backwards. But as we let this run and run and run, we have this flashlight from the left has remained on. After some duration of time, it matches exactly what's at the top. Now, if we use a frequency domain simulation, that just jumps straight to this steady state response. A time domain simulation, which was down below, shows you everything leading up to that steady state response. And then, of course, you see the steady state response at the end. So times where that transient response is of interest, a time domain simulation is your best solution. Time domain solution of the heat equation. So we always start by setting up our problem. So let's say we have some bar and it's made of some strange material that actually changes as down the length of the bar. And so this alpha is called the thermal diffusivity. You can think of it as like an optical density, or sorry, not optical density. I'm an optics person. It's stuck in my head as a thermal density. And so it really sort of characterizes how quickly heat would pass through the material. And so that's changing as a function of x along the bar. So it's a thin bar. So we have what is essentially a one-dimensional problem. Here's how we're quantifying the thermal diffusivity as a function of a distance along the bar. And so we're holding one end on ice. So this end is held exactly at 0 degrees centigrade. And at some point at time 0, what it would normally be, we're going to apply heat to this end and hold this end exactly at 350 degrees C. So on that end, at time 0, it will go immediately from 0 to 350 degrees C. Question is, what does the temperature look like across the bar as a function of time? So first we need the governing equation. This is the time domain heat equation. So T will be temperature. That's a function of X, and so we'll have a different temperature at every position across the bar. Of course, we already said we have this thermal diffusivity that's changing across the bar from one side to the other. Little t is time, and then we have our del operator, which is a three-dimensional derivative. This del squared is a three-dimensional second-order derivative, so you can kind of think of it as measuring curvature of this temperature. And the second-order del operator is actually called the Laplacian. And just to give some numbers here, here's what the thermal diffusivity looks like for a bunch of different materials. And of course, we know intuitively heat will travel very quickly through metal, and that has the highest thermal diffusivity, or it's the most dense medium. As it gets less dense, it takes heat longer to travel through that. So that's our heat equation. That's what we want to solve. First thing, we really have only a one-dimensional problem. Yes, truly it's three-dimensional because that bar has some size, but if that bar is pretty thin, typically we can solve this very accurately as a one-dimensional problem. So let's take our heat equation and expand this into all three dimensions. And so what changes is this Laplacian, this del squared, and that's what this expands to. It's a scalar Laplacian. Now, if this is truly, well, it's truly three-dimensional, but if we can accurately reduce that down to one dimension, the bar is going in the x direction. That has to mean that whatever's happening in these directions, in the cross-section of the bar, is not important. And we can just drop them out of the equation. So what we're left is really what we would call the governing equation for our problem. That's the equation that we're going to solve, not the equation above it that has y and z in it. This is only a function of x and time. Now that we have our equation from the previous slide, the first thing we want to do now is approximate all of the derivatives with everything we know about finite differences. So we have a first order derivative with respect to time, and we have a second order derivative with respect to x. Let's go ahead and approximate this with finite differences. So we'll just make a guess at this. So we have our time derivative, we have our future temperature profile minus our previous temperature profile or current temperature profile divided by the time step delta t. That's a first order derivative. No derivative happening to our thermal diffusivity, so that just comes down here. But we have a second order derivative of the temperature with respect to x. So here's how we approximate a second order derivative. And it's the temperature at the next point minus 2 times the temperature at the point x plus the temperature at the previous point, all divided by the grid spacing squared. Let's look at this in more detail. Let's figure out where each term exists in time and space. So the last term, everything we know about finite differences, if we look at that, we can say, oh, we have this, it's symmetric about x, so it exists at x, and we're not messing with t anywhere in here, so everything exists at time t. So that term exists at position x and time t. Our thermal diffusivity term, it doesn't have time in it, so we can just say it exists at time t, but it exists at x. Now let's think about this term. Well, nothing's happening with x, so it exists at point x, but where does that term exist in time? Well, if we're looking at this as a central finite difference, it actually exists at a time t plus delta t over 2, because that's midpoint between t plus delta t and just t. So this term exists at a different instant in time than the other two terms in the equation. So this equation is inherently unstable, or at least could lead to instabilities. What do we do about that? So one way we can handle this is we can look at this time derivative and let's call it a backward finite difference. So that means it actually would exist at time x, or time t and position x, at the same instant in time and space as all the other terms. Okay, now we cheated a little bit. So by doing this, we cannot call this formulation unconditionally stable. There will arise circumstances where this can go unstable, even if we've done everything correctly. So there's a danger here, but also great simplicity. If we can get away with this, that's really cool. Very similarly, we can just rearrange time a little bit. We can call this first term a forward finite difference. That would still exist at x and t. Cheating again, it's not unconditionally stable, and probably the simple one to go with is just solution number 1. Well, what if I want this unconditionally stable? Well, what we would have to do is let's keep our time derivative this way. We want to do that because we're iterating over time and we're going to have to handle this time derivative a little bit differently. But what if we take our second order derivative and actually add it at time t plus delta t and divide by 2. So we're really averaging that derivative at the current time step and the next time step. So we are interpolating that term at the intermediate time step. So now this interpolation actually does exist at time t plus delta t over 2. That makes this entirely thing unconditionally stable. This is the best and healthiest way to do it, albeit it's going to be a more complicated solution because now we have more terms. So this, by the way, is called the Crank-Nicholson scheme. Unconditionally stable, but it leads to a more complicated solution. And sometimes we have to do this. In this example, we can actually get away with solution number 1, and that's what we'll proceed with. So we will go with solution 1 because I think it's the simplest, and this will work for us. So the first thing I like to do is not write my finite difference equations this way, because I want to solve things on a computer, and I want things in terms of array indices and not, physical position x and physical time t. So let's write the same equation a little bit differently. So our time step now we're going to call k. So k is going to go 0, 1, 2, 3, 4, 5, all the way through our simulation. So the actual time t, if we needed it, would be that integer time step k times delta t. Very often we don't actually need this, but if we did, that's how we interpret it. And our position x on the grid will now be array index I. So don't confuse that with square root of -1i. This is the array index of position I on the grid. So this is the final form of our finite difference equation. From that, we want to derive the update equation. So what we see is that there's only one term that exists at the future time step. So we're going to solve this equation for this term. When we do that, we have what's called our update equation. And we'll notice that t at the future time step equals t at the previous time step plus a constant times some information. And in fact, this is our sort of our second order derivative. We're going to write our update equation this way. Remember all the constants that collected into C. Those aren't changing as a function of time. So we will calculate those ahead of time. And we call those the update coefficient. It is a function of position because the thermal diffusivity can change as a function of position. That's why we have an array index I here. So we'll calculate this ahead of time. Our update coefficients will be an array. So really, if we look at this update equation, there's a unique update equation for every point on the grid. And in this case, the only difference is this update coefficient is what changes. But really, we think of every point on the grid as having an update coefficient behind it. And when I take one pass across the grid and apply this update equation to it, I am taking temperature values from time t to time t plus delta t. And then if I go through the grid another time, now I'm at t plus 2 delta t. And I keep doing that. I keep making these passes through the grid to update everything to the next time step. Now there is a stability condition here, and let me just step you through this and you will see why. Notice how we derived our finite difference equation. It's a term that's coupled to immediately adjacent terms on the grid. This means if I was to inject a number at one point on the grid, it's absolutely impossible for that number change to travel past one cell in one time step. That's just due to how my finite difference equations are. Now, if my finite difference equations were higher order, and maybe they reach 3 or 4 cells out into the grid, this isn't necessarily the case. But ours only reach one cell over, so it's impossible for information to travel farther than one cell in one time step. So I can sort of write the velocity in our finite difference method, or the maximum velocity, is one cell in one time step. Now, the physical wave, the speed of heat, is sort of a controversial thing. Some people don't even like that concept, but we can roughly write it this way. It's the thermal diffusivity over this delta x parameter, our grid resolution. And so in a one-dimensional medium, that is approximately the speed that heat will travel. Now, if the heat had to travel, let's say I've calculated my time step incorrectly, and the heat would actually have to travel 5 cells in one time step. My finite difference method can't do that. It can only travel 1 cell in one time step. So if the physical wave ever outpaces what is numerically possible, the simulation will go unstable. So we need the speed of the physical speed of the heat to be slower than what is possible with the finite difference method. And that's really what the stability condition says. We want the actual physical speed of heat to be less than what is possible numerically. Now I've stuck in a factor 1/2 to be a safety margin. And so let's proceed with that. The first thing we'll do is we'll take those equations from the previous slide, throw them in here, and now I want to solve for the delta T. So given my thermal diffusivity, given the resolution on the grid, this gives me sort of a maximum value for delta T to keep my simulation stable. And I can have any delta T from that value smaller. So we will call that the stability condition. When we get to electromagnetics, there's a very similar stability condition because we don't want the physical wave to outpace what is numerically possible. So here's our revised algorithm given everything we've just gone through. So we will initialize MATLAB, close figure windows, clear the command window, clear memory. We enter the dashboard. We're defining all of the simulation parameters. We will define the thermal diffusivity. We'll define maybe the resolution of our grid. All of the hard-coded numbers go here. We'll then calculate our grid. We'll figure out how many cells we need on the grid, and we'll also figure out the size of the cells, dx, on our grid. Once we have our grid, we can go ahead and build the device on the grid. In this case, it's assigning a thermal diffusivity at every point on the grid. So we might call that array alpha. And alpha will be an array with nx elements in it, a different alpha for every point on the grid. Applying the stability condition, we'll calculate what is a stable time step. So we'll calculate the time step dt, and maybe even calculate how many time steps we want. Right before we enter the main loop, we need our update coefficients. These are where all the constants had collected, and every point on the grid has its own update coefficient. We'll initialize our temperature across the whole grid to be 0. Notice there's 2 arrays here, and that's because as I'm updating from left to right across the grid, I don't want to have a grid that has new values on the left and old values on the right, because now when I'm doing these updates, I might be involving half old values, half new values. I don't want to do that. So when I store my temperature in an array T, I will put all of the new values over to T2, then just copy them over to T and keep doing that. I don't want to have equations that are mixing new and old values. I want to use all old values to calculate the new values. Now we enter the main loop. This is where we're iterating over time. And if we plot what happens here, we can actually watch the temperature wave or temperature front creep across the bar. So we will update T all the way across the grid. So we're setting up a loop, something like for little nx equals 1 to big NX. And we apply the update equation at every point. Once we've updated all the way across, we will enforce the boundary condition. So for us, that means the temperature at the left is 0 and the temperature at the far right is 350 centigrade. We might record intermediate results if we want to. We might want to visualize the intermediate results. I always do this when I'm doing time domain simulations. I don't want to wait till the end to look at things because what if something's going wrong? What if my simulation takes a week? I don't want to wait a week if I can tell something's going wrong in the first hour or two. So I always like to visualize my results, intermediate results. So we run this main loop over and over and over until finally it reaches a steady state or the simulation's over. And at that point, we post-process the results to learn whatever it is we wanted to learn. And of course, the very last thing, visualize that. Don't just provide arrays of numbers. I don't want to look at the number temperature across the bar. I'd like to see a nice plot of it. And that's it. We're finished. And that's how you would implement a time domain finite difference method. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.